So this next problem says two isotopes of carbon, carbon-12 and carbon-13, have masses of 19.93 times 10 to the negative 27 kilograms and 21.59 times 10 to the negative 27 kilograms, respectively. These two isotopes are singly ionized plus E, and each is given a speed of 6.667 times 10 to the fifth meters per second. The ions then enter the bending region of a mass spectrometer where the magnetic field is 0.8500 Tesla. Determine the spatial separation between the two isotopes after they have traveled through a half circle. Okay, so a mass spectrometer. We have these images here from the book, and I just pulled up some information here. So it says mass spectrometry. Spectrometry is an analytical technique that measures the mass to charge ratio of charged particles and so on. And it says molecules, chemical compounds, mass to charge ratio, and so on. And then I scroll down here to applications, and there it says isotope dating and tracking, trace gas analysis, atom probe, pharmacokinetics, protein characterization, all kinds of applications. Glycan analysis, you can come up with lots of stuff that mass spectrometry is used for. Chemists, biologists, in forensics, in lots of fields where you can imagine that this kind of method would be used. Okay, let's look at this one here. Up here it says plus E. By the way, that does not mean that this one is a positive electron. Positrons do exist, but what this means is that it has a charge of 1 electron charge, except it's positive. And what that usually means is it is an atom that may look like follows. One moment. So that we have an atom here with protons in there and with some neutrons in there. There we go. And some electrons around there. So there are electrons around here. And there's just one proton. Oops, didn't mean to do that little thing here. There's just one proton more than there is an electron, and that would make the whole thing to be positively charged. So the charge of this one here is 1 electron charge. The mass of it, well, depends on what the problem is about. Okay, let's see what happens here. So here's the particle, the atom, that is apparently starting at a positive plate and then is being shot towards a negative plate, respectively. Not, I take that back, it's not shot, it's attracted by the negative plate. After all, if it's positive, it will be. There's a little gap in there, it goes through here, and then it enters the region of the magnetic field, and that is where it's deflected. Now let's look at the right hand rule. The thumb is telling us that the positive particle is going up, then the fingers are telling us that the magnetic field is coming out. And I'm trying to do this here in my office with my hand. It's really difficult to turn my hand around so that it's actually pointing out of the screen. I really get a cramp in my hand when I do that. And then the force coming out of my hand is pointing towards the right of the particle's path, and it makes sense. In this case, we have a positive charge, so it is being deflected to the right. Okay, and then depending on its mass, it will make a smaller circle. If it has a larger mass, the force won't be as strong. I'm sorry, the force will be there, but the acceleration isn't going to be as much. And if it has a smaller mass, then the acceleration is going to be larger, and we get a wider circle, semicircle, and they want to know what the difference is here in separation between these two. Okay, let's see how we're going to do that problem. First of all, there is actually kind of a curious equation in here that actually doesn't appear in the problem, but when you go all the way back to chapter 18 on the electric potential energy, you find that the charge times the voltage equals the electric potential energy. and that would be in this case the kinetic energy. And now watch what happens. Both of these carbons would have the same charge. Both of these carbons would see the same voltage. And as I said, this one here is then the kinetic energy. There's 1/2 mv squared. And now the problem says something very curious, and that says they both have the same velocity. Well, if you can imagine the two carbon particles, isotopes, have a different mass, that cannot be true. So they, as far as the problem is concerned, it'll work. I'm just pointing out that they should technically have different speeds, and our algebra should work differently, but we're just going to say, okay, this is the way it should usually work. It's just that in order to make the problem, I guess, more simple, they kind of leave this out here. We can definitely do the problem, and we will. One of the things is that we have a magnetic field here coming out of the paper that influences the particle and puts it into a semicircle. So we have a centripetal force acting on here. And that I would have to combine with the force exerted by a magnetic field. The Lorentz force, you don't find the word Lorentz force in the book, but usually you could look it up. And they already did it for us in this particular chapter. So I did the algebra before. I'm not going to do it again. It's R equals the mass of the particle times velocity divided by the charge and divided by the magnetic field. Notice on the right hand side everything is given. I'll mention them in just a moment. First of all, the mass here is what I want to mention first. The mass of a carbon isotope, and this would be carbon isotope. I'll write this again. Let's see what they say in the problem. Carbon 12. Which is given as 19.93 times 10 to the negative 27 kilograms. So they just throw this at us. However, let me show you where that actually comes from. Okay. So 19.93 10 to the negative 27. I'm going to divide this here by the mass of a neutron, which is given as 1.6749 10 to the negative 27. And the reason I use a neutron is because the carbon isotope 12 has 6 neutrons in it. That would make sense. It has 6 protons in it, and it has 6 electrons. And if you look at the masses, proton and electron mass combined give you roughly, or pretty well, the mass of a neutron. So that's why I divide by 12 by the mass of the neutron. Almost gave away my answer here. There it is. In fact, there it is. 11.899 rounded 12. You would think that this should be an integer 12, but a couple of things are happening. One of them is that there's one electron missing on this particular isotope, and the other one is that some of the energy, some of the mass goes into the binding energy between the protons and neutrons and neutrons and protons, neutrons, and so on. So that's why it's not exactly. Notice the other number that they give us for the carbon 13, which they give to us as 21.59. gives us the rounded 13, and again, because it's not exactly the integer, because some of that mass goes into the binding energy to hold the nucleus together. And again, one electron is being removed. So that's where these two masses come from. Okay, now what we have to do is plug in the numbers. So for the RC12, I'm going to take this one off here and rewrite it. The radius for carbon 12 and the mass for carbon 12. All I have to do now is plug in these numbers: 19.93 times 10 to the 27 kilograms times velocity given as 6.667 times 10 to the 5 meters per second. And keep in mind that they give us these velocities here, both of them for both of them being the same, while actually with a given voltage they should be slightly different, but we accepted that they want to give us a slightly easier algebra here than it already is. Divide by the charge of the particle, which is a positive 1.602 times 10 to the negative 19. Divide also by the magnetic field as given in the problem as 0.8500 Tesla. Notice that you get 4 significant figures. So here you're going to come up with a radius and I might as well do that. So 19.93 10 to the negative 27. Oops. I hope you caught that earlier when I wrote this down. Sorry if it confused you there, but you could imagine that I don't want to record this whole thing over because I made a typo there. Alright. So negative 27 times the given velocity of 6.67 10 to the 5th, meters per second, divided by one positive electron charge times the given 0.8500 Tesla, and I come up with this kind of radius. This would be in meters, so 0.0976 is the radius. Okay, and then I do the other one. So this one, the only thing that changes now is 21.59. There we go. Enter. Divide these two from each other. So this one here minus the 0.0976228978. Enter. 0.0081 meters, but this one here is a radius to the left, a radius to the right, so it's one full diameter. So I have to multiply that answer by 2, because here on the first one, oops, didn't mean to click there. On the first one, they separate by that amount, and then on the other side, they also separate by that amount again. So the total answer is 0.016 meters, or 1.6 centimeters, approximately 2/3 of an inch. I did find one animation for that. Let's see, I think it's this one. There we go. So here is a positive particle that is coming out, and there's a certain voltage here, negative apparently, so the positive particle will be attracted, and then there's a certain magnetic field coming out of the paper, and then I shoot it here, and there it is. And here all I can do is change the magnetic field. So when I do that, I guess make it stronger. Then it shoot here, and the radius is smaller. Or I could make the particle faster. No, I can't make it faster, I can only make it slower here. So you will see that therefore that circle is also smaller. I could change the magnetic field, and then of course when I turn the magnetic field around, the particle will be curved towards the left. Okay, let me see if I can go back to the original. There we go, hits right in there. Change the magnetic field a little bit. Fortunately, in this one I cannot change the mass of the particle. And do it again. Oh, it doesn't show me both records at once. Okay. Okay, just a little bit more on this problem, as I just noticed. Of course, we would still have to calculate what the radius is for the other one, for the carbon 13, and then we would have to subtract these two here and come up with the difference between these two here. But that's already what I did on the calculator. So the difference between the two, and again, just like I did on the calculator, that would have to be multiplied by 2. So subtract and then 2 times that delta R. Alright, the next problem says a proton with a speed of 3.5 times 10 to the 6 meters per second is shot into a region between two plates that are separated by a distance of 0.23 meters. As the drawing shows, a magnetic field exists between the plates and it is perpendicular to the velocity of the proton. What must be the magnitude of the magnetic field so that the proton just misses colliding with the opposite plate? So that, of course, means that, let's see, actually before I say that means, let's see actually in which direction the force is. So the velocity of the proton, positive particle, is to the right, so that's the direction my thumb points. Then the magnetic field is into the paper or the screen, so that means that my fingers are pointing into the screen, and then my hand is pointing up, so the force in this picture here is upwards, respectively to the left of the particle. And unlike a previous problem, actually I can hold my hand really nicely. In the previous problem I had to cramp it up, I had to really turn it, but here it's really nicely, so it points up. And then what it means is that we will come up with a semicircle here and curving around. So let me try to draw that here with my left hand. I always use my mouse with my left hand, so I can write with my right hand. So I guess that's my semicircle there. And we would have to assume that the region, that the plates are actually larger than this one here, and the magnetic field region reaches out there. So basically what that means is that then the separation between the two plates is also the radius. So the radius of this semicircle is, what was it again, 0.23 meters, right? And it's basically plugging these numbers into a given equation. Again, what do they want to figure out here? What must be the magnitude of the magnetic field? So we just use that equation where they have figured the centripetal force equals the force due to the magnetic field, and they wrote R equals mv over qb respectively. In this case we're supposed to figure out the magnetic field, so it's a magnetic field equals mass times velocity divided by the charge of the particle and the radius. Again, everything is given in standard units, so we have to come up with the standard unit for the magnetic field, which is Tesla. The mass in this case is the mass of the proton, given in the front of the book, and I'm sure it's at least once or twice or more times in this chapter as well, being the mass, the mass of the proton being 1.67 times 10 to the negative 27 kilograms. The velocity is given in this problem, right? Being 3.5 times 10 to the 6 meters per second. The charge of the proton is just the opposite charge of the electron, so it's positive 1.602 times 10 to the negative 19 coulombs, and the radius is given in the problem as 0.23 meters. So again, just a matter of plugging in numbers.